Assalamu alaikum. This is Dr. Qusay Faisal with you. I'm going to continue and proceed about computer architecture design. Actually, after I give you introduction last lecture about the computer architecture, and also I talked with you regarding Moore's law. If you remember, I told you that Moore's law shows that the processor is going to be increased double every let me say roughly every 2 years or every 1.5 year, and the registers, the memories, is going to increase to double every 10 years. That study started since 1972 or something like that, and still this formula or this graph up to today date. So this is the Moore's law, see here. So this is regarding the central processing unit, CPU, and this is regarding the memory. I told you that every 10 years is going to be double. So after I finished that, and I told you at the end that computer design divided to instruction set design and computer hardware design. Today lecture I'm going to talk about instruction set architectures and the arithmetic logic unit. Before I start with this one, so I will go to show you I'm going to show you the instruction set architecture as I'm going to explain it. So let me say if we have a formula like this. So what is instruction set architecture going to do with formula? Instruction set architecture actually is like a bridge. It's like a bridge between hardware and the software which is going to execute this hardware. So it's going to arrange what is the computer to do and how the computer think. So let me say we have this formula here, or this equation, C equal to A plus B. So what is instruction set architecture is going to do? How it's going to arrange it? First of all, is going to check about the operation code. It's going to put operation code, going to find how many operation code, maybe one operation code, maybe two, maybe many more than that. Okay, then it's going to find the address for variable for the data A and for the data B. It's going to put the address of data A, and then it's going to put the address for data B. After that, is going to find the location where it's going to execute this program. So it's going to make a range address of destination. Address of the destination is the address where it's going to execute this formula. Thus, as a simplest way to explain the instruction set architectures. Another way, I could simplify it like this picture. See here, this picture. There are two people dancing to each other. So this is like a software. And there's a person, or there's someone or something supporting, holding all the operations. So this is the hardware and the execution program, which is by the way is central processing unit. So instruction set is the link between this software, those two dancing people, and this hardware. That's instruction set. So now, after I explain it in simple way, so let's go for instruction set architecture's definition. Instruction set architecture definition is the attribute of system as being programmed as by programs such as the conceptual structure and functional behavior, as I explained before. As a separate from organization the data flow and control the logic design and physical implementation. So that's the definition of instruction set architecture as I simplify it here. Exactly. Now, in order to design instruction set architectures, we need to know certain things. What we do need to know. Firstly, we have to know how many number of operation we have. One number of operation, two number of operation, how many number of operation we have. So define how many number of operations, number of instructions. So you do need to organize of programmable storage for that. So in order to store it in them. So we are going to store the number of operands here. Okay, that's number one. Secondly, the size of the functions. So is it fixed size or variable size? So these functions, these A and B, are fixed or variable size. So for that, data type and data instruction, data structure is required. Thirdly, we have to instruction format. We have to look for instruction format and instruction set. Fourthly, we have to know how to access to the data. So there are two ways to access the data. Is it we are going to access from memory or from register? So addressing mode is important in this one. Finally, the locations of operand. So where we are going to save, where is the address which we are going to save the operation of operand, the location of operand. So here, for example, C equal to A plus B. So where we are going to save the results of A plus B, where we are going to save C. So the location of operand or location of operation is required to know. So that's what we need for designing instruction set architectures. Now, the most important things here, the person who support this one is the central processing unit, is CPU. The time, so if the time is shorter, so that means you have powerful CPU. If time is longer, so you have normal CPU, not powerful. So here the equation which you do need it for central processing unit time is this one here. So you have to know how much instructions you could do per one program. You multiply it by how many cycles you are going to proceed per one instruction. Finally, you have to multiply it how many seconds you do need to proceed one cycle. So instruction per program times cycle per instruction times seconds per cycle. If you see here, cycles is going to go with cycles, instruction is going to goes with instruction. So what is left here? Seconds per program. So the central processing units, the time required for central processing unit is how many seconds per one program. So that's the speed of central processing units. Now we are going to go for embedded circuit program, which is required for instruction set architectures. The main embedded set program for instruction set architecture is structure name von Neumann diagram. This one have been done since 1950 or between 1945 and 1950, done by person named John von Neumann. That's John von Neumann. He is Hungarian. He was born in Hungary, and he graduated from university in German. Then he traveled to Washington D.C. in USA, and he lived there. And he designed the first computer in the world. That's which is after that's the structure have been done for first computer in the world. Actually, first computer in the world, it's what was up since 1964. So something like 10 years after designing this diagram, so the first computer happened. It was the size like half room, you know, 4 meters by 4 meters, something like that. It was a huge size, and it's doing simple calculation program. So that's what it was. Anyway, that diagram, it have been developed or issued since 1950, and is still used up to now for all the computers. So as you see here, if you look to the structure, so this is the main memory. The main memory is going to link with arithmetic logic unit, so it's going to take and give information between the arithmetic logic unit. The arithmetic logic unit is going to take and give information with central processing unit. So the central processing unit is also linked with the main memory. Now the arithmetic logic unit also linked with input output. So that's the structure of von Neumann diagram. So see here, this is stored program concept. So the main memory storing, so this is the main memory storing program and data. And then you have arithmetic logic unit operand on binary data, of course. So I'm going to use binary data. Then you have a control unit. This is the control unit, interpreting instruction from memory and executing. So see here, interpreting from memory and executing through arithmetic logic unit to input output. So that's how it's going to deal. So input output equipment operand to control units. So a control unit through arithmetic logic units. So that's how it's going to work. Then the registers, the set of registers for von Neumann diagram is done in something called Institute of Advanced Study, so IAS. So that's the register for von Neumann diagram. How it looks like. So the register of von Neumann diagram is like this. If you see here, so this is the input output, and this is the main memory. So the input output, it will goes to the buffer. So this buffer is like some register. A buffer is kind of register to store the information which is received from input output. So that's buffer called MBR, which is memory buffer register. Then memory buffer register is going to deal with memory address register. So MAR. So what is MAR? MAR here, memory address register. Sorry, the memory buffer register is going to deal with this one, accumulator register, and it's going to deal with multiplier accumulator through arithmetic logic unit. So this is arithmetic logic unit. So there is accumulator here. It's going to help the arithmetic logic unit. Then the memory address register is going to deal with memory through this register. So it's going to give the information whatever whatever the memory buffer register to IBR, which is instruction buffer register. This instruction buffer register is going to hold, so it's like temporary register, is going to hold instruction that is coming either maybe it's coming through memory through MAR or through MBR. So this memory, this is kind of another register to storage. As you remember, we studied in the microprocessor about registers, and we say it's kind of temporary memory that is going to store some data. So that's these types of registers. In exam, I might ask you to draw the von Neumann diagram. So this is the von Neumann diagram, and I'm going to ask you to draw the Institute of Advanced Study, IAS. So for the registers for IAS. So the registers for IAS, this is the draw. And also I am going to ask you, of course, you have to give the name for the registers. What is MBR? MBR is memory buffer register. This is, you do need to memorize it. MAR, what is MAR? So this is MAR. What is MAR? Is memory addressing register. IBR, what is IBR? This is buffer, instruction buffer register. What is the PC? There is here PC. What is this one? Is program counter. So I will not ask you what is each register going to do. So when I ask you to draw the registers of IAS machine, okay, so draw this drawing, and you give them the abbreviation of it. So abbreviation of MBR, abbreviation of MAR, abbreviation for IR. So this is IR. What is the abbreviation of IR? What is abbreviation for PC? So no, I will not ask, I will not require to give what is each register going to do. Okay, just draw the registers of IAS, which is the registers for von Neumann diagram, by the way, and you give the abbreviation or the name for each register. That's it. I will not ask you for definition for each register. It's not required. So that's the main things you should know, because this is the computer days, the execution program, the execution program for all computer these days. So from all time, from 1950s up to now, that's what is going to use for computers and calculators. Now I am going to go for arithmetic logic unit design process. So for arithmetic logic unit design process, there are three processes, which is design. First of all, we have design presentation of a project. Secondly, we have to design begins with requirement. Thirdly and finally, we have to design finish as assembly. So what is design arithmetic logic unit process? How you design it? Actually, this is going to be designed using VHDL program. This program is not required for you in bachelor degree, but if you continue for master degree and you be specialist about processor, this program you must, and you do need to know how to program this one. Actually, it's kind of this program is kind of hardware and software. Hardware, you have to, first of all, you have to put a graph. This graph shows how many input and how many output you have. So you have to design a representation of an object. So first of all, you have to traditional craftsman. That means you have to put a graph, representation of classes. You have to draw a graph. Then on this graph, you have to show how many inputs and how many outputs you have. So separation comes because of the complexity. So you have to separate your work. How many graphs you do need? 2 graphs, 3 graphs. So first of all, you have to simplify your work, because complexity, that's the final things, but you have to simplify it. How many graphs you need? So first of all, you have to put the graphs. Secondly, you have to put how many graphs you need. Each graph, you have to give what's the object. One of the graphs, for example, you want to add 3 numbers, 4 numbers, addition. Second graph, you want it, for example, for multiplication. Third graphs, you don't need it for logic, something logic. So you have to put how many graphs you want. Then use that. By this, you put the graphs and you simplify it from complexity. Then you have to put object for each graph. So this graph was going to do. Then finally you have to process intersection design. So each graph you have to put how many input, how many output, and then how you are going to link between these graphs. So that's design as a representation of a project, and that's only this we are going to do it, or we are going to see it. The rest we are not going to proceed it. So design begins with requirements. So you have to functional capitals, what you will do, what it will do. Then performance characteristics, so what is going to perform: speed, power, area, cost, so all these things. Then design as a finish, as a simply. So this is final. So design understood in terms of components assembled. Then top down, so there are two: top down decomposition, and bottom up decomposition. Top down is of complexity functions, so you have to look at it as a functions. The difficult functions is going to simplify it. The bottom up composition, this is the final. That's for final look. So how is going to be function in the final. So primitive so the bottom up composition of primitive building block into more complex assembly. So you are going to see this one bottom up, you are going to see from the final results all as a one component. All these components you are going to combine it, and you are going to see it as a one component. That's bottom up. You are going to see the final results. We are not going to practice this one and this one, because especially this one, the design finish assembly, we are going to see it after applying the software program called VHDL, which as I told you, are not going to practice this one as undergraduate study. This is for master or PhD study. So I'm going to start with give you example about design representation of an object. So here, design refreshment as an object. So what you are going to do, first of all, we are going to do informal system requirement. So what you need, what you want to do. Then you are going to go initial specification, how many input you have, how many output you have. Then you are going to do intermediate specification, you are going to draw the graphs. Final architecture design, so you are going to put the final design, so you are going to put the inputs and output in these graphs. Then intermediate specification and implementation. Then final internal specification, how you are going to link between these input and output, and how you are going to see the results. Then you get the equipment. So this is physical implementation. Physical implementation, when you get the equipment and you link between the input and output. That's what we are going to focus. This work, which is design refreshment, which are this one. So this one, the flow chart of this one is design refreshment of an object, is this one. This is the flow chart. Now let's go for example. Let's do example about this. Before I do for example for that, here it says explain how design, this is example actually, explain how design involves educated guess and verification. First of all, you have to give goals, what you are going to do. So this give goals by what you are going to do with this design, what you are going to do, what is the benefit of this design. So how should this is prioritized. So which one is going to come first, what you have to do first, okay, and what you are going to do, what is the goal, benefit of this design. You have to secondly give an alternative design pieces. So if this design is not success, so what is the alternative should be? And then you decide which one is the best. Given design space of component and assembly, which part will yield the best solution. So which part or which design is going to give you the best solution, and you are going to choose. Now I think we are going to go to the next slide, which is example. Here the example. Example here we want to do, for example, we want to design addition between two binary number. Each number. This is register. So this is register, and we want to design two number. One is 16-bit, and the result is S. Okay. The carry out is C out. So every summation or every addition, so it should be there is a carry out. So what are the input? The input is two operates, A and B input. What is the output? Is 1-bit output. So I am going to design, I'm going to the solution. So that's the question, and this is the solution here. The solution start from here. Okay. So what I want to do, I want to design a gate do addition for two numbers. So what I have, for this I have to decide how many input I have. If I follow here, number one, so I have to draw the graphics and separate outcome complexity, the object of relation. So then I have to object of relation, and then process of intersection design. This is finally thus design as a refreshment. So first of all, I have to design graphics, but before graphics I have to decide what's input and output I have. So I do need to decide, because addition, so I do need two inputs, variable A and variable B, and I want to have how many mode. Is it 3-bit or is it 4-bit? So here 3-bit. Normally this is because it's hexadecimal numbers, so I do need 4-bit mode. However, when I decided to design 3-bit mode, so that means I have two numbers from 0 to 7, each one from 0 to 7, although that is hexadecimal numbers, but the hexadecimal from 0 to 7 only, because the mode of the function is 3-bit mode. So from 0 to 7, from 000 to 111. So the inputs I have 2-bit of hexadecimal A and B, and I do need to have 1-bit of mode, which is 3-bit of mode function. Okay, 3-bit of mode function. For the output, I do need this is 1-bit carry out. This is wrong. 1-bit carry out. This is not input. This is out. 1-bit CN carry in. So CN, this is important, and we are going to find out the CN as an input. What is going to do? I think we are going to find it not next lecture, maybe the lecture after the next lecture. So when we are going to design, no, actually next lecture, when we are going to design full address and half address, full adder and half adder. So when we are going to design, this is next lecture, you will find it more easily to understand why we do need CN. CN is to carry signal. So in case you have a minus, you add two numbers and you have minus, this is carry in. So we are going to find it out in next lecture, why we do need CN. So for designing, when you add two numbers, you do need two input and 3 mode functions, This is a 3-bit mode function. This is because you want to count two numbers from 0 to 7 in this case, and you do need input as a cin. For the output, you do need the summation output, which should be, if you have hexadecimal input, so the output should be same hexadecimal 16 if you have 16-bit, so this is 16-bit. And you have cout in case you do add two numbers and there is carry, so this is to be cout. So I draw the arithmetic logic unit and I draw the inputs here. See here, I have two input variables. These are the variables, and this is the mode function, and this is the cin, and I have two output. I draw it. So after that, I have elements of design. The element of design is divide and conquer formulas. Thus it will be used the software VHDL software, which we are not going to do it. So so what I want you to do, so maybe I will give you as a subtraction. So what subtraction you do need? Of course you do need two input and you have one output, but what else? What other modification you have? Do you need cin or not? Do you want cout or not? Of course no cout for subtraction. Okay, so what about the signal? If you subtract two numbers and there is signal in minus, so what you are going to do? How you design it? So this is the design of arithmetic logic unit, but you have to figure out how many inputs you have, how many outputs you have in your design. So that's design as a refreshment, and that's only what's required. It's not required element of design process. This one is not required because this is software. So I will not ask you to design this. Now for next lecture I am going to explain about the arithmetic logic unit for half adder and full adder. But before that I have to explain about how the arithmetic logic unit to calculate plus and minus. Actually there is no minus, no subtraction in arithmetic logic unit. If there is subtraction, if there is, for example, a minus b, actually the arithmetic logic unit is going to do a plus minus b. It's not going to do a minus b straight away. It's going to do a plus minus b. Actually what's happened is the arithmetic logic unit is going to take b, and it is going to take 2's complement of b and add it with a. So a minus b is going to take a plus the 2's complement of b. So actually there is no subtraction straight away in arithmetic logic unit for computer. So it's going to take the 2's complement of the second number if the second number is minus. For that I want to explain a little bit about the binary, how to do addition and subtraction in arithmetic logic unit. I know you took it with Dr. Qasim, with Mamusta Qasim, or during logic operation. Mamusta Qasim, or maybe Dr. Ammar, he give you the logics. So I think with Dr. Ammar, you took it already with Dr. Ammar, the logic design, how to add and how to do 2's complement. But I am going to remind you, just a quick reminder. So if you have a 3 plus 2, for example, so how to do it, to do this in binary? 3 in binary is actually 0 0 1 1. 2 in binary is 0 0 1 0. So if you add this and this, so 1 plus 0 is 1. 1 plus 1 is 2. 2 actually is 0, and there is remainder 1. And then 1 plus 0 is 1, and 0 plus 0 is 0. So the total will be 0 1 0 1, and this is in binary, that means is 5. So if you add 3 plus 2 in binary, so it's 5. If we take another one for addition, if we say 3 plus 3, So 3 is 0, 0, 1, 1 plus 3, which is 0, 0, 1, 1. If you do addition for that, so 1 plus 1 is 2. So 1 plus 1, 0, there's 1 remainder. Then 1 plus 1 plus 1 is 1, and there will be 1 remainder, because the 3 is 1 and 1 remainder. Then 1 plus 0 is 1, and 0 plus 0 plus 0 is 0. So 0, 1, 1, 0, that's equivalent to 6. So that's for addition. Now let's come for the subtraction. As I mentioned, subtraction in binary, it takes 2's complement. What is 2's complement? 2's complement, for example, if I have, for example, number, let we say 0, 0, 1, 1. What is the 2's complement of this one? 2's complement for 0, 0, 1, 1 is b-twist this number. So instead of, I'm going to replace 0 with 1 and 1 with 0. So 0, 0, 1, 1. I'm going to b-twist it, so it will be 1, 1, 0, 0. Then takes 2's complement by adding 1. So this is, if you see here, 0, 0, 1, 1. What if you b-twist it? It will be 1, 1, 0, 0. If you add 1 to this one, so add this one plus 1, so it will be 1, 1, 0, 1. So this is the 2's complement for number 3, which is 0, 0, 1, 1. And that's what we are going to use it. If we, for example, if we say number minus 3, so we are going to put this value here. Now, if you add two number, let we try something. We have example here. 7 minus 6. What is 7 here? 7 is 0, 1, 1, 1. This is binary. So I cannot put minus 6. So actually is 7 plus minus 6. There is no minus 6 in binary. So how you do minus 6? I have to b-twisted minus 6. What is 6? If I come back up a little bit. So this is 6. Where is 6? Here 6. 0, 1, 1, 0. So I have to take 2 complement of 6. So how to do it? B-twisted. B-twisted, I change all 0 to 1 and all 1 to 0. So it will be, instead of 0, 1, 1, 0, so it will be 1, 0, 0, 1. So I'm going to put 1, 0, 0, 1. Then I have to add 1. So 1 plus 1 is 0, and there is 1 left. So 1 left on the top here. And here the 1 plus 0, so it will come down. So it will be 1, 0, 1, 0. And that's the value of 2's complement. See here, this is 2's complement. So 1, 0, 1, 0. So I have to do 7 minus 6, actually 7 plus the 2's complement of 6, which is 7 plus 1, 0, 1, 0. Let me see here. 7 plus 1, 0, 1, 0. 7 here plus 1, 0, 1, 0. That's the 2's complement of number 6. So 1 plus 0 is 1. 1 plus 1 is 0, and there is 1 left, remainder. Goes up. 1 plus 1 plus 0, so it should be 0. 1 plus 1 is 0, and 1 remainder. 1 plus 1, 1 plus 0 plus 1, so 0. And 1 left. Because there is 1 left, Yekmawa. So that means the results of this addition, because when you added it to 2 complement, so the results, because there is 1 left, 1 remainder at the end, so that means the results is a plus. So the 1 remainder shows that the results is a plus. So the result is plus 0, 0, 1 or plus 1. So that's the results. Be careful. So if the operation of the results, there will be at the end carry 1, that means the results in plus. Now what if the results of adding with the 2's complement of number, there is no remainder, what a remainder near, nothing mawa. So that means the results should be in minus. Now look here, 3 minus 3, 3 minus 5. So actually computer or in binary, So you don't, there is no minus, so it should be 3 plus the 5, 2's complements of 5. So 3 is 0 0 1 1. What is the 2's complement of 5? If I go up and the slide up, 5 is 0 1 0 1. So first of all, I have to B-twist this number. B-twist this number, change all 0 to 1 and all 1 to 0. So this one, it will be 1 0 1 0. So this is 1 0 1 0. That's the B-twist of this number. Then after that I have to add 1. Add 1 to 1 0 1 0. So it will be here 1. So it will be 1 0 1 1. So the 2's complement of number 5 is 1 0 1 1. So 3 plus the invert or 2's complement of 5 is 3 is 0 0 1 1. The 2's complement of 5 is 1 0 1 1, as I explained in previous table. Do addition for these two numbers. So it will be 1 plus 1 is 0 and there is remainder 1. 1 plus 1 plus 1, so it should be 1 and the remainder is 1. 1 plus 0 plus 0 is 1. And here is 0 plus 1 is 1. There is remainder? No, there is no remainder. That means that the results is negative. So because there is no remainder, so the results must be negative. We put negative. And after we put negative, I have to take the 2's complement of this one. After putting negative, because there is no carry out left, nothing mawa, so I have to put minus here because there is no carry out, and I have to take the 2's complement of this one. The 2's complement of 1 1 0 1 is 0, so B-twist this number, it will be 0 0 0, and the invert of 0 is 1. Then after taking the B-twist of the number, I have to add 1 to become 2's complement. 2's complement, you have to add 1. So 1 plus 1 is 0, and there is 1 carry out or yek mawa. Yek plus yek is 0 and yek mawa. Yek plus 0 is yek. So this yek is going to come down here. And then there is ever 2 0. 0 plus 0 and 0 plus 0, it is going to go here. So the result is minus 0 0 1 0. So which is minus 2. You have some exercise here. You could find out. This is practice for you. It's not required. It's not homework. So practice for you here and here. Sorry. Here, and you have some exercise for practice here. So you could practice on these numbers here. By the way, in the exam I might tell you to add two number. I give you two number and one of them may be in minus. So this is easy and you should know it. So if it's minus, you have to take 2's complement for the second number. And if there is carry out, so the result is positive. If there is no carry out, so that means the result is negative, and you have to take the 2's complement of the results. So there is some examples exercise here to practice. So finally, the functional specification of arithmetic logic units. So what is arithmetic logic unit is going to do? Arithmetic logic unit could add or subtract numbers. So that's the benefit of arithmetic logic unit. Either is going to add or subtract numbers. It's going to or it's possible to use logic gates like X, OR, AND. So all these logic gates, it's possible to do it in arithmetic logic unit. Also, it's possible to put, for example, set for less than or more than. Okay, it's going to by use it the 2's complement and compare between two numbers. Okay, now what is the design of arithmetic logic unit? So this is the design of arithmetic logic unit. If I told you draw the design of arithmetic logic unit, so you have to draw this and this. This is the design of arithmetic logic unit. You have to draw this first and this is the next, because this is shows. Now this is arithmetic logic unit. and it shows these are the inputs, and this also the input for the how many bits for these numbers, and these are the outputs. All these are the outputs. So that's the arithmetic logic unit design, and this is the design inside. The design inside is look like full adder with mixture, with multiplexer, sorry, full adder with multiplexer. So that's the design of arithmetic logic unit from outside and from inside. If I told you in the exam, draw the design of arithmetic logic unit, so this is the drawing of the design of arithmetic logic unit. If I told you that what is the benefit of what is the specification function of arithmetic logic unit, so these are the benefits or specification functional specification of arithmetic logic unit. Now that's it for today's lecture. Thank you for listening. If you have any question, either you could send it to me through the Google Classroom, or you could meet me anytime in my office. I am available from Saturday to Wednesday from 8 a.m. to 2 p.m. if I don't have a lab. Actually, I have mostly every day labs, either in our department or in accounting department. However, anyway, if you have a question, I am ready to answer. Thank you for listening. Good luck to all.